Here's one quick look again at Bayes' theorem using count by count understanding. So we did one numerical example, including looking at Excel, how we can tabulate it nicely, perform quick tabulations, and then easily arrive at the final answer. We stress efficiency, so I didn't really explain much about why. And knowing why is not so crucial, to be honest, to get the numbers right and then interpret those posterior probabilities so as to help us make better decisions. However, knowing a little bit about what is going on and why it works the way it works is very helpful because it uses conditional probabilities. It is having some sort of a mutual exclusivity and exhaustiveness kind of discussion. So it reinforces our concept. And then we will revisit and reuse our probability definition by using the count of interested events over count of universal events. So here, to begin with, we are given the count of number or area of I1 inside S2. Let's just talk about I1 in S2, right? Forget about I2 for the moment. So I1, this part, this section, all right, this section, right, inside S2. So the proportion of this I1's blue section inside the S2, the entire S2. So we are given just the area, like cm square or something like that, just the area, no division, right? So count of it inside S2. This is the given. What we want is the left side. Count the amount of S2 inside I1. Now that is sounds like the same, but it's not exactly the same. This is what we are interested in. This is what we are given. All right. So someone looking at I1 can tell us this proportion, but then we stay in the S2 world. We wonder what is this this area here inside S2. So agree with me that counting the area of S2 inside S1 is the same as counting the area of I1 inside S2. Just change the word inside to be intersect. Then we know the commutative behavior, or and, A and D, right? So it doesn't matter whether you change left to right to left. Now, if we agree to that, then let's agree to this. On the left side, I divide by count of I1, yeah? Earlier on, we had 3 and 4, right? We just add them up. So count of I1, that's 7. That's one figure here. But on the right side, I should divide by count of I1. But I'm going to split the count of I1 into count of the I1 inside that of S1, which is the 3 that we talked about just now. I think it's 3 or 4. Okay, 4, because it's a bigger area. And plus the 3 that we put, that the I1 is inside S2. So it is mathematically the same as far as the denominator is concerned. But what is interesting now is that on the left side, all right, it's beginning to look like a conditional probability, right? So we just change the inside, the word inside, into intersect because it's commutative. You can swap them and that doesn't change the meaning. So we're going to change all the inside words into intersect. Yeah. So far, so good. It's looking a little bit more mathematical, but doesn't change the meaning at all. But what is nice is that, look, on the left side, it is exactly fitting our definition of the conditional probability of S2 occurring given I1 has occurred, right now. So we can change that into this symbol. And what was counting earlier on now becomes a ratio, a probability, something abstract, right? And that's the beauty of it. We went from counting to something that we cannot really fathom easily, at least for beginners, right? So on the right side, I'm going to do some mathematical tricks, which is very simple, kind of like divide by 2 on top and divide by 2 below. So I divide by count of universal set, whether it's 100, 50, doesn't matter. So and then below, I divide all the terms by count of universal set. So that's fine, right? No problem. But then, what is interesting now is that I can multiply and divide by count of S2. Why would I want to do that? So when I multiply and divide by count of S2, more because there's a S2 component here. And you know how I'm trying to drive it towards, right? So if I have a denominator that is count of S2, then this term is going to look like the conditional probability of I1 occurring given S2 has occurred. Can you see that? Yeah. And because of the universal set here, we can change this fraction into probability of S2. And that's the prior probability. Brilliant. Yeah. So even though this seems redundant, but putting them in solves a lot of problem because it introduces a new concept called conditional probability and then the prior probability. And that's exactly what happened in just the final and the last line here. Yeah. And then also at the bottom, because count of I1 intersect S1 divided by C of U, what that gives us is just probability of I1 and S1 happening together. That is not an input. That kind of probability is not something we can experimentally easily derive. So while that is mathematically equivalent, it's not in a very useful final form yet. And that's the reason why we are going to times C of S1 divide by C of S1. So that sounds like making it more complicated, right? Not really, because when we do that, we get this concept called P of S1, which in reality is a prior probability that we can easily scan and count the number of S1 happenings based on all the 100 days. Remember in our example about the Wall Street Dow Jones plus and minus example, right? So P of S1 is quite easily estimated. And then we have C of I1 intersect S1 divided by C of S1. But hey, that is just conditional probability of I1 happening given S1 has occurred. We can write it down as a notation like this. Then we do the same for the other side and we realize that, hey, this is the final form of Bayes' theorem where, check this, on the right side, everything is given S1, S2. And on the left side, this is given I1, which is back to the very useful form of predicting the future, right? When the expert says S1 is going to happen, what's the chance that the reverse occurs? Yeah, so this is exactly why Bayes' theorem works out very well, just based on how we count, yeah, the relevant sections in this universal set.